let's take a look at this last example here, just to try to tie this in. The hypergeometric distribution can actually be closely related to, and maybe even approximated by, the binomial distribution. And this is the kind of question where that's going to come into play. So let's take a look at what we have here. It's estimated that 3,000 of the 10,000 voting residents of a town are against a new sales tax. So 15 eligible voters are selected at random. What's the probability that at most 8 favor the new tax? Now, naturally, this should be a hypergeometric distribution question, okay? Because what are we looking at here? 3,000 residents are against. So of the 10,000, there are 3,000 that are against. Then that would mean if there's 10,000 residents, 7,000 are in favor. Right? You're going to select 15 voters at random. All right, so this, if you're picking out 15 voters at random at once, this is like sampling without replacement. So we should use a hypergeometric distribution. What's the probability that at most 8 favor the new tax, right? This is at most 8 favor the new tax, but let me just quickly think about what would be the probability that x is exactly equal to 8. What is the probability that you get exactly 8 that favor the new tax? Well, in this case, you have 10,000 voting residents, and you're picking a sample of 15. Already, you might see the problem. 10,000 choose 15. Complicated to compute. Or not complicated, maybe, but it's large to compute, right? And then think about your success probability here. At most, favor the new tax. There's 7,000 people in favor. In this case, I'm just saying this would be 7,000 choose 8, 3,000 choose, whatever. What's 15 minus 8? 7. Okay, these combinations aren't going to work very well because, for example, 10,000 factorial, pretty large when you start to break up the combinations into factorial. So this is problematic, all right? That's problematic. So how does this relate to the binomial distribution? Well, think about one of the fundamental differences being sampling with replacement versus without replacement. Okay, if I am getting a probability that at most 8 favor the new tax, if I select one of the people, so there are 7,000 people, and I take one person. So there's currently at the first person, for the first person in the sample. For the first person in the sample, there's a 7,000 out of 10,000 chance that that it's favored. There's a 7,000 out of a 10,000 chance, right? Or a 70% chance that they are in favor of it, right? What about the second person? If this is sampling without replacement, well, the second person, if I'm just going to say this is an order, well, that would mean if the first person was in favor, the second person, there would be 6,999 people left that are in favor out of 9,999 people that you're picking from, right? So what is 6,999 divided by 9,999? That is basically 70%, right? This is 0.69996. That's basically 70%. What about the third person? What if you take a look at the third person? Well, that would be, there's 6,998 people left in favor. There's 9,998 people left in the total population. So 6,998 divided by 9,998, that is 0.69993, which is approximately 70%. Okay, so in this case, when the sample size that you're picking from is extremely small relative to the total population size here, right, you can almost treat our probability as constant. All right, so we're going to go ahead and answer this question and approximate it with a binomial distribution. If 7,000 people are in favor, we're going to treat this as a constant success probability P of 7,000 over 10,000, or 70% success probability. Q then would be 3,000 over 10,000, or 0.30, right? Our failure probability of voting residents are against. 3,000 people are against. That means 7,000 people are in favor, and we are concerned with the probability that we get at most 8 people are in favor of the new tax. So if X is counting the number of people that are in favor, we want the probability that X is at most 8, that's less than or equal to 8. Okay, X is less than or equal to 8. And we're going to treat this as a binomial probability question. We're going to sum over the binomial probabilities with a sample of size what? This is a sample of size 15, success probability 0.70, as X goes from 0 to 8. This is a cumulative distribution problem, so we can look up this value in the table here. R is 8, N is 15, and our success probability is 0.7. So let's go ahead and do that. Take a look at the table here real quick. Where's my table? And 15, N is 15. Let's see, that might be on the next page of our binomial probability sums here. Let's see, is it down here at all? Might be the next page even. Yeah, 15 there. Okay, so here we go. Table A1, 15. How many successes were we getting? It was at most 8, I believe. It was at most 8 with a success probability of 0.70. Here we go. At most 8. Follow the row here. Bingo. 0.1311. Approximately 0.1311. It's an approximation, but since the true probabilities would only change, so far out, we can say that's probably relatively accurate. So about 13%.